Good afternoon, everyone, or perhaps good morning if you're joining from the European time zone. I hope you enjoy Simone's talk as much as I did, and he probably saved me a little bit of time trying to convince you that atomic force microscopy is actually a quite powerful technique in unveiling the structure and properties at extremely low scale. So in this talk today, I would like to show some recent advancements in ultra-high resolution atomic force microscopy that could be achieved on the ambient atomic force microscopes. As Simone probably mentioned in his previous talk, AFM has some very serious advantages in high resolution imaging. And the idea of high resolution imaging, or the sort of achieving high resolution, is actually very essential to different areas of science. In the previous talk, we saw that being applied in biology and biochemistry, but that is also happens in all sorts of other scientific areas. For instance, I'd like to give you a quite different sort of view on things. For instance, if we look at an entirely different science, which is astronomy, and look at the beautiful Iris Nebula I took some months ago from my garden, you see a central star and some nebulosity. And for many years, people were convinced that that dust around the central star was just nothing but a space dust. And then when astronomers in 2005 imaged a very small, or in other words, from the high resolution imaging of the small area of that nebulosity with the Hubble telescope, they observed that that nebulosity has a structure, and within that structure, they observed not only scattered light, but emitting light from the small areas. And then it took another few years till Spitzer telescope took infrared data, much like Simone did with his proteins. But in this instance, they discovered fullerenes, or C60 molecules, in the space dust. And that was the first observation of C60 molecules in the space, which was quite exciting. And that small story, which has not much to do with the AFM, shows you a very important principle in science. The more you look, the more power you have in your technique to look at the object, the more you see, the more details, the more properties you can unveil. And today I'm going to walk you through some AFM advancements on how you can actually improve your resolution, both structurally and functionally, to actually see those small objects in their molecular beauty. So first, I'd like to emphasize why atomic force microscopy is such a powerful technique. And I'd like to give you a few very important points on that. First, it provides with a real space imaging. Unlike typical structural techniques that usually provides us with the diffraction data or images in reciprocal space, AFM and scanning probe microscopy in general gives us real space images, meaning we can actually see molecules, we can see atoms and how they interact. It also provides us with the real time and real space dynamics, meaning we can actually see how those molecules move, interact, and so on. And that could be done in virtually any environment, from ultra-high vacuum all the way to physiological liquids. Then the AFM is a highly localized technique, and that is because we're using ultra-sharp probe with the tip radius down to a couple of nanometers to probe very small areas on the surface. So we're actually measuring from under the tip of a tiny area. It is also damage-free. You don't need to destroy your sample to determine the structure and measure the properties, as happens with some other techniques, for instance. Another important advantage, much like real space imaging, is functional imaging. So not only you can measure the structure, you can probe some properties. And for instance, Simone showed how you can probe some mechanical and spectroscopic properties. So you can measure infrared spectrum from that tiny area on the surface, from whatever object you're looking at. And critically, AFM in principle has limitless resolution. So there is no real limit to how far you can push the technique. And that's been demonstrated on sort of different occasions where people imaged almost atoms in molecules, but that was done in UHV. And the centerpiece of the atomic force microscopy is the probe, is an atomic AFM tip, as we call it. And here's a TEM image of the very end of the Mod 75 cantilever that was used in many of the works that I did. And the interesting thing here is if you look at the inset, the tiny one with the 5 nanometer scale bar, you can see some small roughnesses on the sub-nanometer scale. And those roughnesses actually help you to achieve the resolution that I will be talking about. So go into resolution. I'll give you a quick historic overview in terms of how the technique was developed. Perhaps the first most sort of reproducible approach to achieving high resolution that could be done routinely. It was introduction of torsional tapping mode by Nick Mullen and James Hobbs a few years ago here in Sheffield in the UK, where they used T-shaped cantilevers to observe molecular defects and single molecules on the polypropylene and the polyethylene lamellas and so on. Then there was introduction of bimodal tapping, where people sort of observe similar structures. And then the technique I sort of developed some years ago, and that's been applied now to quite a lot of different systems, is so-called high Eigen mode imaging. So the first example of that was done on the polythiophen, where we could observe single CH3 groups on the semi-crystalline surface of the polymer. Then it was obviously extended to some other polymers. An example here is a tactic polypropylene, and so on. If we look at that technique in brief, it basically consists of exciting the cantilever, a standard cantilever, nothing really special about it, but you excite it at a higher Eigen mode. For instance, if you use a standard cantilever and excite it to the first or fundamental Eigen mode, the motion looks like a hammer. So it's your first Eigen mode. When you move to second Eigen mode, or third or fourth, and occasionally can go all the way to the fifth Eigen mode, the shape of cantilever oscillation is quite different. For instance, the sketch here on the right shows the motion of a cantilever now in the third Eigen mode. So the actual part of the cantilever that moves becomes like really small. And instead of using large, well, for instance, 200 micron cantilever, it shortens down to around about 15 or 20 micron cantilever. And because of that, the apparent stiffness of cantilever goes up, and it actually, for the third mode, is in several hundreds of newtons per meter, roughly around about 600 to 700 newtons per meter. And that in turn allows you to use ultra low amplitudes that otherwise are absolutely inaccessible in ambient, because the cantilever tend to stick to the surface. So when you excite to those high Eigen mode, you can use tiny amplitudes because of the way the cantilever oscillates, and that helps you to achieve high resolution. And to give you a quick idea of why that approach is so special and unique is, first, you don't need any special cantilevers. You can use any. You don't need to change anything in your microscope. You just use whatever you have. It works great both in air and liquid, and it can be applied to virtually any sample, and on average it provides with a much better resolution. So in terms of resolution, I'll give you some examples of high resolution that could be achieved. In this instance was achieved on Park Systems large sample NX20 AFM. Couple of examples from the molecules. For instance, we take a trimesic acid that forms a nice hexagonal structure on graphite surface, and we can nicely image that network. I'll talk a little bit more about that further in the presentation. Same, we can image a much smaller network made of melamine cyanuric acid with a period of 9.8 angstroms only. But those samples are usually atomically flat samples, and it's a bit easier to achieve resolution on them. If we move to real world samples, for instance, real world polymers, a piece of polypropylene plastic that used for packaging, we can achieve equally good resolution. We can see single molecules, single polypropylene molecules forming those lamelles, and we can zoom at the edge of the lamella and can see the molecule going in and out of that lamella, which is quite exciting. Again, it's a real space imaging. You can see the molecule under your tip, and that's the beauty of that technique. Okay, and then another real-world polymer, Teflon, a piece of Teflon tape that everyone uses quite often. And here we achieve a 5.6 angstrom resolution. That's the distance between PTFE chains taken in ambient, and so on. Of course, it's not limited to just polymers. You can image things like moire patterns on graphene and other 2D materials, and you can observe those beautiful moire patterns. As Simone said, it's extremely important to use AFM in biology and biochemistry to look at the biomolecules. And here's an example how we observe the molecular structure of peptide nanotubes made of short peptide diphenylalanine and so on. So this is a sort of a brief example of various high-resolution images that could be achieved in ambient with that high eigenmode approach, and those examples were taken on a next one to a large sample AFM. Okay, so first let's talk about imaging molecules and surfaces. Why is it so important? First, when you adsorb molecules on some surfaces, you can change the chemistry, so it's a controlled chemistry. You can also control the molecular adsorption if you use the first layer of molecules to position the second layer of molecules, the third layer of molecules, and so on with angstrom precision. You can also build various 2D organic structures either via hydrogen bonding, like nature does, or via covalent bonding, and approach structures similar to graphene and so on, but with a tunable bandgap, for instance. In the same way, you can build molecular layers one on top of the other, controlling the spatial organization both laterally and in vertically. So let's look at the first example. Let's take a trimesic acid, a very small molecule, just a benzene ring, 3 carboxylic groups. When you put that molecule on the surface, either from vacuum or a liquid, it tends to form that type of a network. Well, it forms quite a few different networks, but that's one of the most stable one. Hexagonal network with the period of 1.7 nanometers. So the distance between those pores is 1.7, and that's the same in crystal and in surface. So let's look at that structure on graphite. So when we put those molecules on a piece of graphite from water, we can observe very nice hexagonal network here. And the interesting thing about the image, it shows you the precise control of forces in those atomic force microscope, because we can observe nicely the edges of the molecular layer and how those delicate structures are preserved during scanning without being destroyed. At the same time, we see different rotational domains. In this instance, they're rotated by 15 degrees. And so, but we clearly observe them as well as the domain boundaries and molecular defects, for instance, like here, where we observe some missing molecules or a few molecules and so on. And we can zoom even further and observe nearly a single molecule of that trimesic acid. Just to remind you, it's a small molecule, just benzene ring, 3 carboxylic acid. And for instance, here in that area highlighted by the white square, it could just make that 6 trimesic acids forming that two-dimensional pore. Okay, we can make things a little bit more interesting. As I said, in atomic force microscopy, not only you can see the real space image, but you can also follow the dynamics, and you can also see how things are changing. Because trimesic acid monolayer was imaged in ambient, and inevitably you have layers of water on the surface because the water absorbs from the atmosphere, and trimesic acid is soluble in water. It was absorbed in water in the first place. So here's the video showing how, I'll fast forward a little bit, how the system changes a little bit, how the molecule diffuse, how, for instance, the protrusion in the layer diffuses compared to the previous one. And that is because we're capturing the dynamics of that monolayer. And at the same time, as we're capturing that dynamics, we also are observing the molecular structure. For instance, now we're seeing another defect forming here at the bottom and so on. But or we can zoom and observe the structure again. But the point is that we observe those structure in real space and real time. For those who are interested, they could watch the video we posted on LinkedIn page as well. So let's move to a slightly more complicated structure. Is a melamine cyanuric acid network, where you take two molecules, again, very small molecules, melamine and cyanuric acid, you put them together, and those molecules form a triple hydrogen bond. And it forms in solution, it forms on the surfaces if you provide a surface for them. And when it forms on the surface, it creates that nice hexagonal unit. And then that structure expands over the entire surface. And the important thing here, that those two molecules, they form only only one structure in that network, and they don't form anything else. And the period for that structure is just 9.8 angstroms. It's quite small. It's twice as less as the previous one. And okay, if we look at that structure, that melamine cyanuric acid structure absorbed on a graphite surface again on a larger scale, for instance, here's a 5-micron image, we see islands observed both in height and phase channels. Interestingly, and that's where the sort of different modalities of atomic force microscopy helps scientists. We can use Kelvin probe microscopy and our version of a sideband of frequency modulated KPFM, where we could resolve domain boundaries within those layers. And that was quite exciting result, because previously KPFM and high resolution KPFM was exclusively limited to ultra high vacuum, and that kind of measurements were completely well, they were thought to be impossible in the ambient, because people thought, well, because you apply the voltage to the tip, it may damage your delicate layers. And those layers are indeed very delicate. Just to remind you, the thickness of the layer here is just 3 angstroms. It's a 1 molecule thick layer. And yet we can resolve the domain boundaries. When we look at the single layers, first we can observe so-called Moiré pattern. That is because the molecular lattice is slightly rotated versus the atomic lattice of underlying graphite. But when we zoom further, for instance, in this square region, we can see both the Moiré pattern, which is 10.8 nanometers, and we're starting seeing the molecular lattice. So in this image, you see actually both. If you zoom further, you can exclusively see the molecular lattice, which is 9.8 angstroms. You can just make the Moiré pattern as well, but that gives you an idea of what kind of resolution you achieve on those very delicate structures in the ambient. Okay. To move to a little bit more interesting things is we'll talk a little bit about imaging biomolecules or some bioinspired structures, and how we can actually achieve some resolution on them to determine their molecular structure. So let's look at the so-called peptide nanotubes. In this instance, they're made from the diphenyl alanine molecules, quite a popular peptide that people have been studying for years, but never actually resolved the structure of those tubes. So here's an optical image taken again on the AF, and you can see those long spaghetti type structures on the surface. They take large scan AFM image, and again you can see those tubes with a length of many tens of microns and thickness of around about 50 nanometers. You can measure their mechanical properties. You can measure things like modulus. In this instance, it's around about 8 gigapascal. And you can measure adhesion as well. But an interesting thing is, as you zoom on top of that peptide structure, and here's the images on the right, you can actually do high-resolution nanomechanical imaging in a so-called pinpoint mode, where you collect fast force maps, and you can resolve some interesting structural motifs in both Young's modulus and adhesion. And I will talk a bit more about what actually we're seeing here. So yeah, so the main question, what is the structure now? So when you zoom further and you take, I don't know, 20 or 25 or something like that nanometer images, and you can take those images along the tube, because remember the advantage of the AFM, not only it's a real space, but it's very localized. So you can go and probe very small areas on your sample or along the tube in this instance. And as you sort of probe along the tube, you see those beautiful lines running along the tube and the principal sort of direction of the tube. And they're very much the same, regardless where you scan. When you take a really small image, in this instance, it's a 10 nanometer scan, you can see those a little bit closer, and we can measure a distance of 1.22 nanometers between those two bright lines. The main question here, when it comes to complicated molecules and achieving high resolution, it's one thing. You can get those high resolution images, but then there is a fundamental question: how do you interpret those results? Because you can't quite see the molecule as the molecule, because they often pack and interact in different ways that you simply do not know. So how to interpret those results, how to attach some chemical sense to that. And there are different ways of doing that. The one thing is to do molecular modeling, and you can run some molecular simulation, like molecular dynamics, for instance, or ab initio calculations and so on. Or you can look at the crystallography data on the similar crystals that were measured in bulk, and that's what I did. I actually found quite a few papers where people looked at the needle crystals of that diphenylalanine molecule, and what I found was quite remarkable. Regardless of the solvent that people use to crystallize those molecules, and here is a THF, isopropanol, and some other, they form very much the same structure, with the molecules running in rows, like on this bottom left image, literally in parallel rows. And when I took the measurement, literally from their experimental data that was published in the papers, the distance between the molecules, or to be precise, the distance between atoms and those molecules, independent of where you measure, is roughly about 1.20 nanometers. And this is precisely what we measure in atomic force microscopy in our ambient experiments. But the critical thing here is that in X-ray diffraction techniques, you measure bulk on many, many, many billions of molecules. Okay. In AFM, you do those measurements locally. So it's a highly localized measurement when you receive that structural information from just, I don't know, tens or a couple of hundreds of molecules. And you can probe that structure locally, investigating some molecular defects or so on. So that's probably the first example of resolving molecular structure on that sort of complicated bioinspired peptide nanotube. So at the end, I would like to stress that the highest resolution using the high Eigen mode could be achieved in a range of different samples, from very delicate supramolecular structures where you can see sort of single molecules and the way they interact. We can achieve it on the real world polymers like polypropylene or polytryphins that I haven't even talked about much, to biomolecules and 2D materials. Not only we can achieve the true molecular resolution or image molecular defects, we can also scan fast and follow dynamics both in air and liquid. And here's two videos. One is showing how we can scan the Mori pattern on the graphite, and I'll just cut there. And the other one is how we can follow the dissolution process of gypsum crystal in water. So and those two videos, they actually demonstrate a few very important principles of AFM. So it provides you with the real space imaging. You see what you image. You can follow dynamics of the imaging in real life, in real time. So that is very important. So at the end, I would like to thank you for all your attention, and remember, science is beautiful. So make it beautiful. So thank you very much, and I'm happy to take any questions you may have.